Welcome back. In the last video, we saw that the model that we've been building has some potential to learn. I mean, look at these predictions. You could get a little bit better, of course, get the red dots on top of the green dots, but we're just going to leave that. The trend is what we're after. Our model has some capacity to learn, except this is straight line data. And we've been hinting at it a fair bit, is that we're using linear functions. And if we look up linear data, what does it look like? Well, it has quite a straight line. If we go linear, and just search linear, what does this give us? Linear means straight. There we go, straight. And then what happens if we search for non-linear? I kind of hinted at this as well. Non-linear. Oh, we get some curves. We get curved lines. So linear functions, straight, non-linear functions. Now, this is one of the beautiful things about machine learning. And I'm not sure about you, but when I was in high school, I kind of learned a concept called line of best fit, or y equals mx plus c, or y equals mx plus b, and it looks something like this. And then if you wanted to go over these, you'd use quadratic functions and a whole bunch of other stuff. But one of the most fundamental things about machine learning is that we build neural networks, and deep down, neural networks are just a combination, it could be a large combination of linear functions and non-linear functions. So that's why in torch.nn we have non-linear activations and we have all these other different types of layers. But essentially what they're doing deep down is combining straight lines with, if we go back up to our data, non-straight lines. So of course our model didn't work before because we've only given it the power to use linear lines. We've only given it the power to use straight lines. But our data is what? It's curved. Although it's simple, we need non-linearity to be able to model this data set. And now, let's say we were building a pizza detection model. So let's look up some images of pizza, one of my favorite foods. Images. Pizza, right? So could you model pizza with just straight lines? Now you're thinking, Daniel, you can't be serious. A computer vision model doesn't look for just straight lines in this. And I'd argue that, yes, it does, except we also add some curved lines in here. That's the beauty of machine learning. Could you imagine trying to write the rules of an algorithm to detect that this is a pizza? Maybe you could put in, oh, it's a curve here, and if you see red and... No. Imagine if you're trying to do 100 different foods. Your program would get really large. Instead, we give our machine learning models, if we come down to the model that we created, we give our deep learning models the capacity to use linear and non-linear functions. We haven't seen any non-linear layers just yet. Or maybe we've hinted at some, but that's all right. So we stack these on top of each other, these layers, and then the model figures out what patterns in the data it should use, what lines it should draw to draw patterns through not only pizza, but another food such as sushi. If we wanted to build a food image classification model, it would do this. The principle remains the same. So the question I'm going to pose to you, we'll get out of this, is we'll come down here. We've unlocked the missing piece, or we're about to. We're going to cover it over the next couple of videos. The missing piece of our model. And this is a big one. This is going to follow you throughout all of machine learning and deep learning. Non-linearity. So the question here is, what patterns could you draw if you were given an infinite amount of straight and non-straight lines? Or in machine learning terms, an infinite amount, but really it is finite. By infinite, in machine learning terms, this is a technicality. It could be 1,000,000 parameters. It could be, as we've got, probably 100 parameters in our model. So just imagine a large amount of straight and non-straight lines, an infinite amount of linear and non-linear functions. You could draw some pretty intricate patterns, couldn't you? And that's what gives machine learning, and especially neural networks, the capacity to not only fit a straight line here, but to separate two different circles, but also to do crazy things like drive a self-driving car, or at least power the vision system of a self-driving car. Of course, after that, you need some programming to plan what to actually do with what you see in an image. But we're getting ahead of ourselves here. Let's now start diving into nonlinearity. And the whole idea here is combining the power of linear and nonlinear functions. Straight lines and non-straight lines. Our classification data is not comprised of just straight lines, it's circles. So we need nonlinearity here. So recreating nonlinear data, red and blue circles. We don't need to recreate this, but we're going to do it anyway for completeness. So let's get a little bit of a practice. Make and plot data. This is so that you can practice the use of nonlinearity on your own. matplotlib.pyplot as PLT. We're going to go a bit faster here because we've covered this code above. So import make circles. We're just going to recreate the exact same circle data set that we've created above. Number of samples, we'll create 1,000. And we're going to create x and y equals what? Make circles, pass it in number of samples. Beautiful. Colab, please. I wonder if I can turn off autocorrect on Colab. I'm happy to just see all of my errors in the flesh. See, look at that. I don't want that. I want noise like that. Maybe I'll do that in the next video. We're not going to spend time here looking around how to do it. We can work that out on the fly later. For now, I'm too excited to share with you the power of nonlinearity. So here, X, we're just going to plot what's going on. We've got two X features and we're going to color it with the flavor of Y because we're doing a binary classification. And we're going to use one of my favorite C maps, which is color map. And we're going to go plt.cm for CMap and red, blue. What do we get? Okay, red circle, blue circle. Hey, is that the same color as what's above? I like this color better. Did we get that right up here? Oh my goodness, look how much code we've written. Yeah, I like the other blue. I'm going to bring this down here. It's all about aesthetics and machine learning. It's not just numbers on a page. Daniel, how could you be so crass? Let's go there. Okay, that's a better color, red and blue. That's more lively, isn't it? So now let's convert to train and test, and then we can start to build a model with nonlinearity. Oh, this is so good. Okay, convert data to tensors, and then to train and test splits. Nothing we haven't covered here before. So import torch, but it never hurts to practice code, right? Import torch from sklearn.model_selection. Import train test split so that we can split our red and blue dots randomly. And we're going to turn data into tensors. And we'll go x equals torch from numpy, and we'll pass in x here. And then we'll change it into type torch.float. Why do we do this? Well, because, oh my goodness, autocorrect. It's getting the best of me here. You're watching me live code this stuff and battle with autocorrect. That's what this whole course is. Am I really teaching PyTorch or am I just battling with Google Colab's autocorrect? We are turning it into torch.float with a type here because why? NumPy's default, which is what Make Circles uses behind the scenes. NumPy is actually used in a lot of other machine learning libraries. Pandas, built on NumPy. Scikit-learn does a lot of NumPy. Matplotlib, NumPy. That's just showing the, what's the word? Is it ubiquitous? Ubiquity? I'm not sure, maybe. If not, you can correct me. The ubiquity of NumPy and test sets, but we're using PyTorch to leverage the power of autograd, which is what powers our gradient descent, and the fact that it can use GPUs. So we're creating train and test splits here with train test split x, y, and we're going to go test size equals 0.2, and we're going to set random state equals 42, and then we'll view our first 5 samples. Are these going to be tensors? Fingers crossed, we haven't got an error. Beautiful, we have tensors here. Okay, now we're up to the exciting part. We've got our data set back. I think it's time to build a model with nonlinearity. So if you'd like to peek ahead, check out TorchNN again. This is a little bit of a spoiler. Go into the nonlinear activations, see if you can find the one that we've already used. That's your challenge. Can you find the one we've already used? And go into here and search what is a nonlinear function. So give that a go and see what comes up. I'll see you in the next video.